Hi, my name is Onkar and I'm studying data science under the guidance of Akash Murthy in Northeastern University. And let's discuss some of the questions. So, the first question is rewrite the elbow in terms of likelihood and prior KL divergence for variational autoencoders and extend the concept to explain how elbow be relevant in the context of diffusion models. Discuss the significance of these forms in both scenarios. Let's break down the concept of elbow and how it's used in VAEs and diffusion models. In variational autoencoders, elbow is a way to optimize the intractable log likelihood. It has two parts: the reconstruction term that helps decoder rebuild the input, and KL divergence term that keeps the latent distribution closer to a normal prior. This combination helps learn unstructured structured compressed representation of data. Now in diffusion models, they aren't explicit latent variables like VAEs, but also still plays a big role. During training, the model learns a reverse a noisy process, and elbow helps guide this by minimizing KL divergence between the forward and reverse noisy steps. In both cases, elbow gives us a principal way to train generative models, balancing accurate generation and behaved latent or noise distribution. It's a core concept that ties together deep learning and probabilistic modeling. Let's dive into the second question. So second question is derive and explain the structure and meaning of beta VAE objectives, including how varying beta affects the latent representation. Let's talk about the beta VAE, a powerful extension of the standard variational autoencoder. In normal VAE, we balance two things: reconstruction, where the model learns to rebuild the input from a latent space, and KL divergence, which keeps the latent space close to a prior like a standard Gaussian. The beta VAE introduces a new parameter beta which scales the KL term. This gives us a control the trade-off between the reconstruction quality and distanciation of the latent feature. When beta is greater than 1, the model pushes a cleaner, more interpretable latent space where each variable controls a separate feature like a shape or a color, but at the cost of the same reconstruction accuracy. When beta is less than 1, it prioritizes the accurate reconstruction but may mix up the latent factors. From an information theory perspective, beta VAE acts like an information bottleneck, keeping only the most essential information in the latent space. Overall, beta VAE is a great tool when you want more structured and interpretable generative models. Now discuss the third question. It's derive the theoretical underpinning of the diffusion process in the diffusion models. Explain how this process contributes to generating new data from a learned distribution. Let's talk about the diffusion models, one of the most powerful generative models today. The idea is simple. We gradually add noise to real data through a process inspired by thermodynamics. This is called a forward diffusion process. After many steps, the data turns into the pure Gaussian noise. The goal is to train a neural network to reverse this noising process step by step, bringing the data back to the bringing a data back from noise. This is reverse diffusion process, and it's modeled using a neural network that learns to denoise the data at every step. We train the model using a variational or lower bound, which helps it learn a distribution close to a real data. In practice, we simply training by predicting the noise added at each step and minimizing the difference between the actual and the predicted noise. That's the simple loss. Once trained, we can start with this random noise and use a model to generate new high quality data like images by denoising it step by step. Diffusion models are grounded in solid theory, combining Markov process, variational inference, and score based learning, making them both elegant and effective. Now, the fourth question is derive the loss function for a Gaussian VAE and showing the components of the reconstruction error and Kullback labeler means scale divergence. Incorporate memory They incorporate the reparameterization trick and its role in the computation of the gradients for these terms. Let's quickly talk about the Gaussian variational autoencoder and its loss function. The goal of VAE to maximize lower bound or elbow. This includes two parts. First, reconstruction terms, which makes the decoder can rebuild the input from a latent vector, and second, KL divergence, which pushes the learn latent distribution to stay close to a standard normal distribution. In Gaussian VAE, we assume that both prior and the approximate posterior are Gaussian. The KL term has a neat closed form formula involving the mean and variance of the encoder. The reconstruction term is often computed using mean square error or binary cross entropy depending on the type of the data. Now, a key trick in training VAE is to reparameterization trick. Instead of sampling the z directly, we write zeta is equal to mu plus variance into epsilon, where epsilon is sampled from a standard normal, and this makes sampling differentiable so we can back propagate through a whole network. In the end, this makes VAEs more powerful and trainable for learning compressed structured representation of data. Now let's dive into the fifth question. It's list all references that were given during the course and what did you learn from each one of them. So the answer is, let's dive into all those 9 research papers one by one. First is autoencoding variational Bayes. It introduces VAE and reparameterization trick for efficient inference in models with intractable posteriors. Enables scalable learning with contiguous latent variables. The second paper is diffusion models, a comprehensive survey. Gave a broad overview of diffusion models covering advances in sampling efficiency, likelihood estimation, and application in fields like vision and NLP. Third paper is hybrid norm. So this paper proposed a hybrid normalization technique combining pre-norm and post-norm for better transform training, stability, and performance, especially in LLMs. The fourth paper is denoising diffusion probabilistic models. It introduces a space-based diffusion model achieve state-of-art image synthesis, linked denoising and lynching dynamics for generative modeling. The fifth paper is conditional GANs. It extends GAN to generate output condition on labels, demonstrated the label-based generation, for example, MNIST digits with class, info, and image toggling. DC GAN. So DC GANs are presented deep convolutional GANs for unsupervised representation learning, showed that CNN-based GANs learn meaningful features and generate realistic images. The next paper is Laplacian pyramid GAN. It combined GANs with a coarse to fine image generation strategy, generated high quality images using a pyramid of convolutional networks. The next paper is generative adversarial nets. It introduced the original GAN framework as a two-player game between a generator and discriminator. The key idea is to adversarial training without Markov chains. And the last paper is improved techniques for training GANs. It proposes enhancement for GAN stability and performance, achieving realistic image generation and strong result in semi-supervised learning. Now, let's discuss the last question. What is the importance of learning GAN VAE diffusion models and transformers in spring 2025, and how did you benefit from this, and what do you intend to do with this? So the answer of the question is, learning GAN VAE diffusion models and transformers has been a game changer for me. These models are at core of today's AI, powering things like image and video generation, language models, and even drug discovery. GAN taught me how adversarial training can produce stunning realistic data. VAE gave me a solid foundation of probabilistic modeling and representation learning. Diffusion models introduce a more stable and elegant way to generate data through a noise reversal, and transformers They have completely transformed how we handle language, vision, and multimodal tasks. Personally, I've grown a lot. I can now read research papers, build and tune models, and apply them to a real-world problems and with confidence. Going forward, I want to develop and creative AI tools, contribute to open source research, and maybe even start off generative AI projects of my own. These models have opened the door for me to explore the frontiers of AI and actually make a difference. Thank you.